Hi everyone, just give me a moment and I'll get things set up so we can take a look at this next video. We've been working our way through Unit 6, Chapter 5, where we're looking at statistical reasoning. In this video, I want to take a look at the second part of z-scores. What we've been doing in this particular section is trying to help you understand what z-scores are, how to use z-score tables, and then we take that information and start to use it to compare data, to make predictions, and to solve some problems. So in the first part of the video, or the first video, which was part 1, we took a look at what z-scores were and some of the basic problems that you might encounter along that line and using the z-score tables. And now I want to take a closer look at the different types of problems that can pop up. So let's go back to the very first example that we discussed when we were talking about comparing the data. One of the very important uses for z-scores is that it allows us to compare values that might have a different mean and a different standard deviation, but be talking about some data set that is similar. So it allows us to be able to compare it. When we were looking at this issue, we looked at this problem. Now, this problem involved a running club. What we're looking at were some times for this running club when they ran a 200-meter sprint in Vancouver and then later in Lake Louise. And we wanted to look at one of the runners' times, Haley's times. We were asking, well, when did she run her best time in comparison with her club's results? So we looked at the results and realized that in both times she ran faster than her club, but it's pretty hard to tell because they have different means and different standard deviations when she actually ran her best time. So z-scores give us a hand with that. And what we do is we calculate the z-score for each one of these scenarios. So in Vancouver, and you'll just have to check the results, pause the video and go back and look. In Vancouver, we discovered that her z-score is negative 1.29. And then in Lake Louise, it's negative 1.33. If we were to put that on a normal distributed graph, we would see that in Vancouver, she was negative 1.29, and in Lake Louise, she was 1.33. And what that's telling us is in Lake Louise, she was further away from the club average. In other words, she was faster than she was in Vancouver. So we can see very clearly, because the z-scores give us a standardized measurement to use, that she ran a better time in Lake Louise. The second thing which we often use z-scores for is to figure out what the probability of the data is, or the information we've been given. So here's a standard question. IQ tests are sometimes used to measure a person's intellectual capacity at a particular time. IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. If a person scores 119 on an IQ test, how does this score compare with the scores of the general population? So we use our formula to figure out what our z-scores would be. It's 119 for the value we're looking at. The mean is 100. The standard deviation is 15. And we find that our z-score is 1.27. Now let's stop for a second and make sure you understand how to find that on the z-score tables. If we look at it, we'll use the first digits, the 1 and the 10th, 1.2, and then we'll go straight across until we get to the 7. So we're seeing that it is 8.8980. And if I go back, that gives me a percentage of 89.8%. Now I can also use this. This is just a close-up of what we did. I can also use this in my calculator. And what you're using is the second VARS button, which gives you the distribution options. Choose the normal CDF. That's the second one down the list. Make sure you put the first value that you're looking for, and that means the lowest one. So if we think about what our graph looks like, let me go back. We're looking for where it was 0 to start with. So we put 0, then we put the number we're looking for, we put the mean, and then the standard deviation. Please notice that these numbers are different. This is more exact. The tables are rounded values. But because one of your outcomes is definitely to help you or to make sure that you know how to read the tables, You have to use the tables in your results. You can always use the calculator to correct your work and make sure that you're in the right spot, but make sure that you use the tables when you're calculating them for assessment purposes. Okay, I think that one's good. Oh, the only other thing I want to say about this is just to make sure you understand what this reading is telling you. We know that our z-score was 1.27, so it's about here. We know that this represents that 89.7% of the data set is to the left of the value. It's always to the left. And that's what this picture is symbolizing, that whatever z-value you take, when you get the probability for it, you're finding the value of the number to the left of your value. Okay, let's carry on. So the next one is where we need to find data values for some reason. So this one was the situation where we looked at the athletes and when they should replace their running shoes. It's a very important thing because eventually the shoes no longer absorb the shock of our weight of our foot. And so especially professional runners need to be careful about this. So running shoes lose their shock absorption after a mean distance of 640 kilometers with a standard deviation of 160. Zach is an elite runner, and he wants to replace his shoes at a distance when only 25% of people would replace their shoes. So the question is, at what distance should he replace his shoes? Okay, so we know that he wants to replace them at 25%. Now we need to look in the z-score tables to figure out what z-score this is. And so we're looking for the number 0.25. Let me just double check and see whether, yeah. Okay, so here I put it. Here's a sort of a snapshot. I'll go back and make sure we know what we're doing. So we're looking for a z-score that is 0.25. Now I do know if it's 25% that is going to be the left of 50%, which means that my number is going to be a negative z-score. So I'm going to zoom in on a section of the negative z-score table and see if I can find 0.25. So I find it here. I notice it's also close to this one, but it's 17 away from this one and 14 away from this. So I'm going to use this one, negative 0.67 as my z-score. Let me keep on going. So I know that my z-score is negative 0.67. I'm looking for what the number would be with a mean of 640 and a standard deviation of 160. When I calculate the math, I should get 532.8 actually in using this z-score table. And so he should replace his shoes at 533 kilometers, about 533 kilometers. Okay. So I believe that's good. I'm showing you the formula there. Here's where you can check it out if you want to actually use your calculator. What you need to realize is that the ordinary normal distribution takes the number and gives you the probability. If you want to go backwards, take the probability and find the number, you're going to use the inverse norm. So you put the probability, notice that you're always using the probability as a decimal version. Then you put the mean and the standard deviation, and you should be able to get your number. Okay, a question about quality control. Here we're looking at making bungee cords. This company produces bungee cords. And if you read through it, you'll find out that the lengths of the bungee cords produced are normally distributed with a mean of 45.2 and a standard deviation of 1.3. Bungee cords that are shorter than 42 or longer than 48 are rejected by the quality control workers. And so the question wants to know, if 20,000 bungee cords are manufactured each day, how many bungee cords would you expect the quality control workers to reject? Okay, let's take a look at this process. First of all, what I did was I took the 42 and I took the 48, and I tried to figure out what the z-scores were. And here they are, negative 2.4 and negative 2.1. Now, what I've drawn is a picture of a normally distributed graph, and I've shown where those marks are. Now, there are two ways that you could actually find this. You could stop and figure out, okay, what percent is rejected over here? And what percent is rejected over there? The values that you would get would be these two numbers. If you add those up together, then you find that 2.27 of 20,000 is rejected, which is 454. Another way that you can do this one is actually using your calculator, and that is to figure out, okay, well, what is the probability of the stuff that's kept? And so I use my norm CDF. I put the lower value in and the upper value, the mean and the standard deviation, and I find that the answer is 0.977. So I take that and use that to figure out what would be kept and subtract that from 20,000 to find that 451 bungee cords are rejected. This is using our calculator. This is using the z-score table. You can use either one. If the directions of the question do not specify, as long as you show your work, it should be acceptable. And then we have some more diagrams of it. This is just another picture of the calculator version. And then we're on to one of our last questions, the warranty periods. A manufacturer of personal music players has determined that the mean life of the players is 32.4 months with a standard deviation of 6.3. What length of warranty should be offered if the manufacturer wants to restrict repairs to less than 1.5% of all the players sold? All right, so if I want to know 1.5%, remember in the z-score tables that will appear as 0.015. So I use my table and realize that negative 2.17 seems to be the z-score. The mean is 32.4 and the standard deviation is 6.3. So I plug things into my calculator and equation, and I find that x is equal to 18.7. So rounding it down, because I really don't want more than I should, I'll have an answer of an 18-month warranty should be offered. And there you have a picture of what we had from that one, but those are some questions to give you an idea of the types of questions you're going to encounter in your homework. Please take a look at the following questions and bring those to class.